Okay, today guys, we're going to talk about the final way to find delta H. It's through bond energies. But before we start, I wanted to kind of review. So we spent almost 2 weeks talking about how to find delta H. We've talked about 4 other ways. What are they? Stoichiometry, calorimetry, Hess's law, and thermodynamic data tables using the standard enthalpy of formation, right? Okay. This is the 5th way. This is the 5th way, and it's finding delta H with bond energies. So, I've saved the best one for last. This one is really cool. I hope you guys will like it. It is a little bit complicated, a little bit different. So please be listening, please be following along. Chapter 4 guided notes. Okay, here we go.
Why do we have to learn that?
Okay, in a chemical reaction, bonds are broken in the reactants, and they are formed in the products. In a chemical reaction, bonds are broken in the reactants, and they're formed in the products. Right? So, does it take energy to break a bond? It does. Energy is required to break a bond. So what that means, guys, is that bond breaking is an endothermic process. Let me say that again. Bond breaking is an endothermic process because it requires an input of energy. So in our reactants, we need to break the bonds because we need to break those bonds so that we can form something new in the products. It requires energy to break a bond. Well, now let's talk about what happens on the product side. Bond formation is an exothermic process because it gives off energy. So it gives off energy. This is important to understand, and I've got a couple of examples right here to show you what I mean. Okay, so let's number these reactions down here. This one's 1 and this one's 2. So let's take this first reaction. I'm going to draw, with bond energies, you got to be good at drawing Lewis structures. So I'm going to do this first reaction up here, and I'm going to draw the bonds. This is fluorine molecule, so it's fluorine with a single bond to another fluorine. Now if we want to draw in our lone pairs, you can. So that's our reactant. We're going to form, it looks like we're going to separate those fluorines and just form 2 fluorine atoms here. So it's balanced. Now, what I've given you before we started this lesson was a bond energy table. I would like you to look up on your bond energy table, how much energy does it take to break this fluorine-fluorine single bond? Okay, so if you look up on that table, what is it? 159. So in order to break this bond, it's 159 kilojoules of heat is required. Kilojoules of energy is required. So it takes energy to break a bond. If energy is coming in, should our delta H be positive or negative? Should be positive. And so that's exactly what this one is. There's no bonds on this side, so the delta H for this process or this reaction is going to be a positive 159 kilojoules. Okay? But what would happen if we took this reaction and reversed it? That's what number 2 is doing. So let's try that. Okay, so now we have 2 fluorine atoms, and we're going to form a fluorine-fluorine single bond. Okay, so there's no bonds here, so nothing is being broken, but we're forming a fluorine-fluorine bond. Again, how much is it worth? How much energy? 159. But when we form a bond, it releases energy. So what do you think the delta H sign is going to be? If it releases energy, it's what?
Negative.
It's negative. This is an exothermic reaction. 159 kilojoules here. And so what I'm trying to do is emphasize these 2 points. When we break a bond, so on reaction 1, we broke this. It's endothermic, so that's positive. When we form a bond, in the product side, we formed a bond here. It's exothermic, so the sign is going to be negative. Okay. Here's the equation that we're going to use to figure this out. Okay, I want you to write this in your notes. So as you're writing it, I'm going to kind of explain it. In order to find delta H with bond energies, so delta H of this reaction is equal to, now we've seen this sigma sign before, it means take the sum of the number of bonds in the reactants, times the bond energies broken, because in the reactants, the bonds are broken. So this is the number of actual bonds in the reactants that are broken. Okay, we take the number and times it by the bond energy. Minus the sigma sign takes the sum of the number of product bonds, and we're going to times that by the bond energies formed. So this reaction, or this equation, is a little bit different than the one we've done before, because you'll notice bond energies broken. This occurs in your reactants. And bond energies formed, this is occurring in the products. Remember when we used the standard enthalpy of formation, the Big Mama equation, we did products minus reactants. Well, this one's different. It's opposite. This is the one that's different. So what I'm going to do is go through and kind of try to explain why it's different. It says, remember right here, it requires energy to break bonds, which is endothermic, and it releases energy to form bonds. So in our reactants, we're breaking them. It takes energy, so it's going to be positive. This is going to be positive value right here. But when we form bonds, it releases energy, which is a negative sign when we're talking about delta H, when it releases energy. So that negative sign is dealt with by putting a negative sign in our equation right here. This negative sign will take care of the sign. All right. What I've got is a quick example to how to do this. So I promise if you pay attention, you keep out your bond energy table paper that I gave you, this will make sense. Okay? So let's follow this reaction, or this equation right here. So my delta H for this reaction is equal to, now when it's written just like this, do we know where the bonds are?
No.
We don't. So we're going to have to become good at writing Lewis structures. And I can help you. As we go through this, I'll help you. H2's Lewis structure looks like this. But how many of those do I have?
2.
2 of them. So I'm going to put a 2 right here. Instead of drawing 2 Lewis structures for hydrogen, I'm just going to put a 2. Plus, oxygen's Lewis structure looks like this. Okay? If you react oxygen gas and oxygen gas and hydrogen gas, you'll make water. Water's Lewis structure looks like this. Okay, now we can see where the bonds are, right? So when we follow this reaction equation right here, are we going to do the bonds broken or the bonds formed first? The bonds broken first. Bonds broken is listed first, so we're looking at our reactants. We've got a hydrogen-hydrogen single bond. This is where you look up the value on this table. What is a hydrogen-hydrogen bond? How much enthalpy is found in that bond? 436. But I've got a 2 right here. That 2 goes for the NR, so I'm going to put a 2 times. This bond right here has a value of 436 kilojoules. Okay? So that's all we do. The sigma sign is telling us to take the sum of all of these bonds that are broken. Well, this bond right here is going to be broken. Okay? An oxygen-oxygen double bond. How many of those do I have? Just 1. So I'm going to put a 1 in right there. How much enthalpy is contained in that bond? How much energy? 498. What that means, guys, is it takes 498 kilojoules of energy to break that bond. Is that all of the bonds that I need to break? It is. So I'm going to close that off with brackets. Now the minus sign. You've got to subtract the bonds that are formed in the products. How many bonds are formed? 2 bonds are formed, so I'm going to put a 2. And they're both hydrogen-oxygen single bonds. What is the value for that?
465.
465. The hydrogen-oxygen single bond. So that has a value of 465 kilojoules. Okay, and that's the only product that we're forming. I've accounted for both bonds that are going to form there. So I close it off. Now it's a very easy math problem. Let's see what it simplifies down to. Okay, so my delta H of the reaction is equal to, let's do 2 times 436, 872, plus 498, minus 2 times 465 is 930. Okay, so now we've got to simplify this one. I'm getting 1370 minus 930. Okay, so 1370 minus 930. And the delta H for this reaction is going to be 440. 440 what? Yeah, if you'll notice on your table, it lists those values in kilojoules. So is this an endo or an exothermic process? It's endothermic. It takes energy. This would take energy. We need to absorb energy for that to happen. All right. What I have discovered as I've gone through and done a few of these is that a lot of chemistry textbooks have bond energy tables. In fact, almost every chemistry textbook you'll see has a bond energy table. But the thing is, they're all a little bit different. Now, they're all pretty similar in the values that are listed here, but in some chemistry textbooks, you'll find a different value. It's going to be close to that, but it'll be different. So, to keep us all on the same page, in this class, we're going to use this table. So, on all of your problems, we're using this one. Okay. And before we move on, I wanted to point out something that you should recognize. What do you think is harder to break, a single, double, or triple bond? A triple bond. So you would think that would take more energy, right? Let's see if that's true. Here's a triple bond, nitrogen. How much energy does it take to break it? 950. Well, now let's just find a double bond. Here's a double bond, oxygen double bond, 498. So obviously, there's more energy to break a triple bond, right?
Yeah, but look at that.
Okay. And now if we find just a single bond, okay, 431. So it did go down. So that's the trend. Single bonds are easier to break. Double bonds are medium. Triple bonds take the most energy to break. They're most difficult. But it does depend on what atoms are involved in the bonding. So we're going to have to look it up, how much energy each bond takes, and put it into that equation. Sound easy?
Yeah.
Okay, let's try one. Practice problem number 23. I want you guys to try this one, okay? It says calculate the delta H for the following reaction. Now, this is methane. We're reacting methane with oxygen. So what kind of reaction does this look like to you guys? It's a combustion reaction. Yeah, we have to have oxygen. It produces CO2 and water. And this is balanced. Now, let me help you out with the Lewis structures. For methane, it looks like this. Now, we've got 2 oxygen molecules. What I'm going to do is just put a 2 right here to remind you to times it by 2. Okay, so there's the Lewis structure. What I want to do is give you some time to try this. Okay, remember, We're doing bonds broken first, so you need to count all these bonds that are broken, look them up on the table, see the value. Here's another bond that's broken. We're doing that minus the bonds that are formed. So these are the bonds that are formed. You need to look at all of those. So I'm going to give you a second to try this one on your own. Okay? Please, if you're watching the video, try it first. Okay, let's see how you guys did. I'm hoping that you wrote down this equation, okay? Delta H of the reaction is equal to, now, do we do bonds broken first or bonds formed? Bonds broken. Okay, so let's do the bonds broken, which are these bonds here, right? Here's what I do to kind of keep track of them, guys. So what I do is put a line through it. So there's 1, 2, 3, 4. There's 4 carbon-hydrogen single bonds. So I'm going to put a 4 right here, because there's 4 of them. Timesing it by the energy that it takes to break them. We look up the energy between a carbon-hydrogen single bond. Where do you see that? Okay, carbon-hydrogen single bond, 414. Okay, now we need to add in the other reactant bond that we need to break. We've got 2 oxygen molecules. Well, in one oxygen molecule, there's an oxygen-oxygen double bond. But I got 2 of them. So I'm going to put a 2 right here. Let's find oxygen-oxygen double bond right here. It's worth 498. Where it takes 498 kilojoules of energy to break it. Is that it for my reactants and breaking bonds? Yeah. That's it. So let's close it off. The minus sign is very important. Okay, so put in a minus sign. Now we come over here and do the bonds form. Remember that bonds form release energy. That's why this negative sign is so important. How many oxygen-carbon double bonds do we have? Well, there's 1, 2 that need to be formed. So I'm going to put a 2 right here. Where's oxygen-carbon double bond at? Oxygen-carbon double bond, 532. So 532 goes right there. Now, we've got to add in these bonds between the water. So I've got a hydrogen-oxygen single bond. But in water, how many are there? There's 2 of them. But I've got 2 water molecules. So how many bonds do I really form here? 4. Okay, so I'm going to take a 4 and times it by, what is a hydrogen-oxygen single bond worth? 465. Okay, is that it for bond formation? It is, so close it off. Now we just got to simplify it. Simple math problem now. Okay, I'm going to simplify this at 1656 plus 996 minus, stay with me guys, okay, so let's simplify it again. 1656 plus 996, 2652 minus, let's do this one, 1064 plus 1860. Did you guys get this, 2924? No. Okay, so let's take 2652 and subtract 2652 and subtract 2924. Okay, so my delta H for this reaction, did you guys get this negative 272? Yes. And what are my units going to be? Kilojoules, because this is measuring in kilojoules per mole. So kilojoules goes right here. Okay, now I've got another question here. It says, why is this reaction exothermic? What does that mean, guys? Why is this reaction endothermic? Or exothermic, yeah. Why is it exothermic?
Because it's negative.
Because the bonds that were formed do they have more energy or less energy? Let me ask that again. The bonds that are formed here, guys, in my product side, do they have more energy or less energy than the bonds that were broken? They have more. That's what's making it exothermic. Okay? They're releasing more energy when they form than it took to break it. Okay. This is the last practice problem. This is the last chance you guys might get to see this. So please, I would like you to try it on your own. Let me help you out with the Lewis structure, and then you guys can get started. So what this is C3H8 is propane. We're going to combust it. It's going to form CO2 and water. Here's propane. Okay, so there's the Lewis structure, guys. I want you to draw that on your notes and then use the equation to figure out the delta H of formation using the bond energy table right here. So please try that on your own, and then once you have an answer, hit play and see if you got it right. Okay, this is a little bit more complicated problem. Let's see how you did. Hopefully you got the answer right. But I wanted to kind of look at it first and predict whether it's going to be endo or exothermic. Guys, this is propane, and when we burn propane, does it release heat or does it absorb heat? It releases. So our delta H should have a negative number, right? Should be negative. If it's not, then we know we did something wrong. Okay, now let's look at it. I've drawn the Lewis structure, so I've got all the bonds here. Let's write our equation. Delta H of the reaction is equal to. Now, do we do the bonds broken or the bonds formed first? Bonds broken, good. So I'm going to put in brackets. Now, these are my bonds that are broken here. Okay, all of these bonds are going to be broken, including the oxygens. So let's go through and count them. Let's do my hydrogen-carbon single bonds first, because there's a bunch of them. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8 of those guys. Let's look up on this table how much energy it takes to break a hydrogen-carbon single bond. And it's right here, 414. 414 kilojoules of energy it takes to break that bond. Now, you might have gone on and you might have missed that there is also this carbon-carbon single bond and this carbon-carbon single bond. So I've got 2 of them. What's a carbon-carbon single bond worth? 368. Correct. 368. Now, that takes care of the propane molecule. Let's go to the oxygen now. It's also a reactant, so I'm going to need to break this bond. It's an oxygen-oxygen double bond. This is just one molecule, but how many do we have? We have 5. So I'm going to times it by what? 5. And how much energy does it take to break an oxygen-oxygen double bond?
498.
Good. It's right here, 498. Okay. Now, is that it for bond breaking? That's it, because that's all my reactants. So I'm going to close it off here. Now what do I need in my equation? What goes here? What sign? A negative sign. Again, because when we form bonds, it releases energy. We've got to have a negative sign to show that it's energy being released. All right, let's look at the bonds that we need to form now. Looks like I'm forming a carbon-oxygen double bond, but how many of them in CO2? There's 2 of them. But how many CO2 molecules do I have? 3. So let's take 3 and times it by the 2. That's in one molecule. And what do you get? 6. And how much energy is released when an oxygen-carbon double bond forms? Good. Oxygen-carbon double bond is 532. Okay. Now we're going to add in. It looks like when we form water, the hydrogen and oxygen are forming a single bond. But in one water molecule, how many of those bonds exist? 2. But how many water molecules do I have? 4. So let's take 4 and times it by the 2. That's what? 8. And let's look up how much energy is released when that bond forms.
It's 465.
Good. Hydrogen-oxygen bond is right here. 465. Okay. Is that it for bond formation? That's it. Okay, so I'm going to close it off with a bracket symbol. Now it's a simple math problem. Okay, let's go through and simplify it. Go slow at this step, guys. 8 times 414 is 3312 plus 2 times 368 is 736 plus 5 times 498 is 2490. Okay. Minus 6 times 532. Good. 3192 plus 8 times 465 is 3720. Perfect. Okay, now let's simplify it. What's in these brackets now? So 3312 plus 736 plus 2490. So 6538 is how much energy must be absorbed in order to break all of these bonds. 6,538 kilojoules of energy must be absorbed. Now, when we form these bonds, it releases some energy. So let's see how much that was. 3192 plus 3720 is 6912. So it releases 6,912 kilojoules when these bonds form. So it's releasing that energy. Okay, we're almost there. The delta H for this reaction is equal to 6538 subtract 6912. Did you guys get a negative 374? Okay, what are my units going to be? Kilojoules, again, because this table is listing those values in kilojoules. Okay. Endo or exothermic? Exothermic. It's negative. It's releasing that much heat. Isn't that what we predicted before? Yeah. It is burning propane. It's going to release energy. This is like a barbecue grill. You burn propane. All right. So, how many of you guys got it right? Good job. I hope that you have learned how to find the delta H using the bond energies. To give you some more practice, this does take a little bit of practice. I've got a worksheet in your student workbook. It's called Bond Energy Worksheet. So please get your student workbook out and go to Bond Energy Worksheet. And let's get that done. And hopefully this video helped.